Welcome back to the class. We will continue where we stopped last time. And I just want to remind you at the beginning that don't forget that we're going to have a quiz on chapter 11 this Thursday. Okay. So last time we stopped at this slide, which is about the contact ratio. And I think I am not going to spend too much time talking about this because we have seen it with our eyes in the simulation at the last class. But basically what we saw last time, just to remind you, and we'll be in the same page, that if we focus on a contact point between two teeth, one pair, and let's say that point started A, as the tooth is moving and the two teeth are moving together, the final contact will be at point B. But what happens, as we saw in the video, that while the first pair are in touch, while the motion is set, after some moment, before the first pair separate, there is another pair which get in touch. And for that reason, we ask the question, is it always the case that only one pair is in touch while the other pair are not? And we said, actually, this is more or less desirable. So to have an understanding about that, we introduced, I don't honestly remember if we introduced this to you or to the other class, but we said that we will introduce here two distances, this arc, which is from the beginning when the first contact is achieved until the center line of the two gears. This is going to be called the arc of approach. This is when they both approach each other. Then they start the contact, move together. And then after the center line, after passing the center line, we will have another arc, which we will call the arc of assess. Okay? This is when they start to separate later. The addition of these two is a QT. This is the sum of the two arcs. Okay. Now, why these arcs are important? Of course, it's because we will define a ratio, okay, which is MC, a contact ratio, which is the ratio of QT, this major arc, divided by P, okay, which is the pitch circle. Now, what you should know is that if QT is 1.2, it means that their pair of teeth, one pair of teeth isn't just entering the contact, and another pair will not yet have reached point B, which means there are more than one pair. Now, what you should know is that, did I forget it here? No. Okay. So you can also measure this MC using the distance LP over there, which is the distance between point A and B measured along the pressure line. And when you divide it by P cosine phi, you will get this ratio, which is a number that indicates the average number of pairs of teeth in contact. Of course, ya shabab, when you have an average which is 1.2, you ask a question, what does that mean, right? What does it mean? I mean, it's a 0.2 teeth. What does that mean? So it means basically, if you can just think of it as this portion of the engagement where there's one pair are now fully engaged. They will continue their journey together from the beginning to the end. And while is that happening, there is another pair which exhausted, let's say, 80% of their contact, and there is still a 20% left. That's how you can think about it. Now, what you should know here, I wrote this in red, is that in reality, we want that contact ratio to be no less than 1.2. Okay? And why is that? This is because inaccuracy in the mounting might actually reduce it. So even if you secure one, you may even have a situation where even the first ratio, the ratio itself is less than 1, which means that there is an instance when there is a teeth in contact, and there is an instant when there are not. This by itself will cause a problem because we will not secure this smooth motion. That's number one. Number two, the teeth themselves are going to feel like, oh, here we are coming in contact and then leaving each other. And then all of a sudden they bump into each other again. And then all of a sudden they bump it. This is going to cause an impact, which is another factor. It's like another load. In addition to the noise and the inconvenience in terms of the motion, the outcome of the motion. Okay, so we want always this overlap to happen. When one pair is about to finish, there is a new pair coming, and then another one. So it feels like continuous. Okay, this is really good. So the other part, which is about that we want to talk about, is about interference. And what is interference? It says here, this is was a little bit changed from the other section. But what is interference, ya shabab? It is the contact of portion of teeth profile that are not conjugate is called interference. What does this mean? First of all, this is scary because whenever you tell me not conjugate, what do you mean? We've been working so hard to make this nice, fancy, amazing profile involute, and we claim that we achieved something really, really interesting by having that involute, and we thought this is amazing, securing a constant angular velocity ratio and so on. So how comes that we don't have that? Well, if you look at here, look at this gear. This is the driving gear. This is the driven gear. Okay, the initial and final point of contact are designated as A and B. All right, and are located on the pressure line. Right, this is the pressure line over there, which is something we know now. صح? While the motion is set, all of the contact point as the gear move is always in the pressure line. That's what we agreed on. Now, notice that the point of tangency of the pressure line with the base circle CD are located inside of point A and B. Interference is present. What does that mean? It means, ya shabab, I'm gonna zoom it in over here. Now, what happened over here is that I'm gonna clean this up.
Doctor, the pressure
so look,
is the line of action.
If we identified, what is it?
The pressure line is the line of action.
Yes, it is the same as the line of action. Okay, now, if we look at the pressure, this is the point, this is point. This is the, the last point of contact where every gear leaves the contact, and then they start the engagement at point A. Both of them located at the line of action, which is the pressure line. Everything is smooth and nice. But if we draw a circle, look, this circle, which encompasses point A, right? This is point A, and this is the domain of point B. So whatever in between A and B, logically, everything here is what? Is an involute profile, and the contacts over here are as much as we want them. But anything beyond that or below it is no. And if you look down below in this example, down below, we see that this gear, look, has a contact over here. And this point is actually below this A point, which means there is a contact down in a location which this portion of the profile is not an involute. You know that, ya shabab, that it is not necessary for the entire tooth to have an involute profile. Maybe, okay, maybe only this portion of it is. The remaining portion is not involute. That's is possible. And you don't care as far as the contacts are happening right there, as we saw them with the gear moving. Why should we care? But if for any reason, the contact reached to this point over there, that's not an involute. Now, what are the consequences? We will not at that instant, tiny little instant. It may come and go quickly, but that tiny little instance, it means that when we are not in the involute, it means there is no conjugate action. It means there is no guarantee that the velocity, the ratio of the angular velocity is going to be constant, and everything is ruined. So this is really a serious matter. We don't want this to happen. So what happened over here is this. We will see, ya shabab, that that one way to secure that there will be no interference. Now, what you should know is that the interference is not desirable. So when you go to the industry, they may tell you, we don't want interference. Yeah. And they may even know a few rules here and there. I'm talking about technician operators, but you, the engineer, knows what's the story. You know it very well. And not only this, you know how to design such that involute is not, interference is not going to be of a concern. So how do we do that? Well, let's have here some relations which are very important. It says that the smallest number of teeth on a spur pinion, we know the pinion, okay, and gear with 1-to-1 gear ratio. So they have the same diameter, except that one of them is the drive, one of them is the driven, okay, which can exist without interference is NP. And this NP is the number of teeth for that spur gear. So what is that number? So we are here to telling you that in order to avoid interference, you can actually pick the gear with a minimum number of teeth, and that will secure that that interference is not going to happen. Okay, so what is this magical number of teeth? Well, it's over here, which is equal to 2 multiplied by k, will tell you what is k, divided by 3 sine square phi. Phi is the pressure angle, and then we have an expression of 1 plus square root of 1 plus 3 sine square phi. Okay, What is K? K is 1 for full depth teeth. And probably most of the time, we will have K equals to 1. But what is a full depth teeth? And what is not a full depth teeth? Huh? Well, if for any reason, any practical reason, you came to the teeth, and this is a full depth tooth. This is one tooth, full depth. Okay? And for whatever reason, I don't know, صراحة, what could be one reason, but you decided that, you see this part? I don't need it. I don't need it. So what did you do? You cut it off. So you machined or you order like that, a gear with which supposed to have a little bit up over there, but you decided that you don't need it. That's called a stub teeth. And if in that case, if this is the case that you have, you should put K as 0.8. Agreed? So what is the story over here? If we tell you what is the smallest number of teeth to avoid interference for opinion, 1-to-1 gear, okay? 1-to-1 ratio. And without telling you, is this a stub or is this a full, then you should assume it full. Otherwise, you will read the word full somewhere in the statement. Okay? And if it is stub, of course, you will be told that. Now, what happens if the mating gear has more teeth than the pinion? Now, here, we don't have this 1-to-1 ratio, okay? And mg, which is equal to the ratio of the number of teeth for the gear divided by the number of teeth for the pinion, which is m, is more than 1. So the number of teeth for the gear is more than the number of teeth for the pinion. In that case, the number of teeth on the pinion without interference is given by this equation. This is very similar to that equation, except that we introduce this m and a few other factors like 2m and so on. Okay, which m is the ratio of the number of teeth. Now, how about the gear itself? If you know what is the number of teeth for the pinion, how about what is the largest gear without specified pinion? With a specified pinion, what is that largest gear? This is it. So in here, you should expect that the number of teeth for the pinion is known, and by knowing the pressure angle and knowing this K4, which is equals to 1 most likely, you should be able to identify the number of teeth for the gear. Now, the smallest spur pinion, like you're talking about spur only, that will operate with a rack. You remember the rack, ya shabab? The rack is like a gear with an infinitely large radius, and we have a spur gear right there. Then if you have that arrangement and you want to secure that there is no interference, then the pinion should have a number of teeth which is equal to 2 multiplied by K divided by sine square phi. Okay? Now, the next part that we want to talk about is the straight bevel gear. Okay, we told you, ya shabab, that this chapter is dedicated for like general understanding of the terminologies and fundamentals related to gears, and we will cover all of them. Then we will have another chapter dealing with each type alone. For now, we are just trying to understand the specifics and fundamentals, terminologies, and so on for each type. Now, for bevel gear, if you recall, as we said this before, we said that for bevel gear, they are usually used when we have intersecting axes like this. So, but I probably told you this before, that if for any reason you want these axes not to be perpendicular, that's also fine. You can just make them like this, just cut the teeth accordingly and they would work. Now, what do we need to know is that if we look at this, ya shabab, what do we have? We have here the pinion and we have the gear based on the convention that the smaller one here is the pinion and the bigger one is the gear. Now, with that in mind, we will introduce the pitch angle. What is it? Well, first of all, you should understand that if you draw the cone, right, because the bevel gear is like a cone, the teeth are cut like this with an angle. So if you continue the projection, you will reach the apex angle over there, and this is just gonna match with the other one, right? This is, if you want, you can call it the front cone. Okay, now for the bevel gear, if you consider looking at this line, which is the line of the shaft, then there is an angle, and there is also another angle, and this angle is called what, ya shabab? It's called the pitch angle. Now, as a convention, since the pinion is the small gear, its angle will be gamma. Why? Because it is the pinion, which is the smaller gear. But for the gear, since it is usually bigger, we will also call the angle gamma, but in capital letter. Now, you may not know this, but in Greek, this is considered a small letter gamma, and this one is considered as a capital letter gamma. Just like psi, like this, and there is a capital letter psi like that. That's it. Okay. Now, so that angle is defined for the pinion as tan gamma, tan small gamma is equals to NP divided by NG, and for the gear, it is tan capital gamma equals to NG divided by NP. Now, shabab, I probably know that it started to get too much, a little bit boring, more equations, more information, and they are scattered. Until now, we don't have a full story of why are we doing this? I mean, is this angle going to be important? Or we engineer mechanical love geometry a lot, and whenever we see two things that are inclined, we create an angle for them. Well, the idea is you have to be patient. I mean, you will need all of this later, and unfortunately, we can't bring later now and have now at now, right, at the same time. So you have to be patient. My advice to you is to have somewhere in your note a section for bevel gear and put all the relation for bevel gear, and a section for helical gear, section for spur gear, and then we'll talk about worm. And you will see that all of these equations, most of them, will become very important later. So there's a whole, go and look at the textbooks. There are whole chapters about gears. So we are not done yet, okay? Now, so what about, I think this is wrong. This is bevel gear. I think I need to fix these things in the slide. Now, what is interesting here is that if you look at the back cone, so we said that this is the the front cone. That's what I told you at least to do. And then if you look at the back cone, which is this one, huh? So you go the other side. You go with the angle of the teeth and you shoot down. And then you go for the other one, which is gonna have a back cone like that, okay? And if you think of that apex angle point over there, where the cone meets to the, you know, the peak point, then, and you look here at the location of the teeth, and you assume that there is actually a circle with a radius starting from the apex here of the back cone until the point where you have the teeth are engaging. Then you will actually end up with some sort of a disc over here. And if you do the same, looking at this as RB, and then drawing this radius where the engagement between the teeth is happening, you will have another one. Now, interestingly, if you think of this as a disc where there are teeth on it, which is like a spur gear, and this is why we have these spur gear drawn over here, have some sort of a virtual spur gear here, an equivalent kind of spur gear. And this is called the Tredgold approximation. And here, this approximation will give you that this virtual number of teeth on that spur gear, which is equals to 2 pi multiplied by RB divided by P. Okay. Now,
Doctor?
Yes?
This virtual number is on the pinion or the gear?
Well, it depends. If you take this radius, it is different than this radius. So depending on the radius that you have.
Okay.
Okay. All right. Now, there is one thing to understand over here. It says that as a standard straight tooth bevel gears are usually cut with 20 degrees pressure angle. So the pressure angle is again 20, unequal addenda and dedenda. These are the plural of addendum and dedendum with a full depth teeth. And you know, it is not stub teeth, it's a full depth. Why is that? It says that these are going to help increase the contact ratio, okay? And you want that contact ratio to be maintained, as we said, because it ensures the smoothness and continuity. Avoid undercut and increase the strength of the pinion. Now, what is the meaning of avoiding undercut? Now, undercut in general, ya shabab, is when for a tooth. So if you have a tooth like this, you can imagine that this is the profile of the tooth. Now, let's say for the sake of fun that this part from here to there is the involute profile, the rest is just a body. Now, the undercut in a simple term means that somebody, while machining the gear, cut this one a little bit more. Now, this, since this is usually not a contact region, it's not going to cause a problem in terms of what? Of motion. But if, God forbid, or for any reason, that undercut trimmed a little bit of the profile, which we want, this is a problem. Another thing, this undercut might cause weakening to the teeth. And this is very bad. So let me explain to you quickly. When in a practical way, you get in a problem with undercut. Let's assume that you are a mechanical engineer who got a job in some company around, I'm not going to name, and then you have an ongoing investigation. There is a machine, there is a tool, there is something, and it is failing prematurely or something happening. And then you decided that, you know what? We need to investigate what is this, what is the property of this material? What is it? Okay. Now, you take a piece of that material, you give it to the machine shop, and you tell them, listen, go and look to the ASTM standard and machine for us samples. ASTM says, in order to secure repeatability of your results, you need to do like 5 to 6, sometimes 8 tests, just to make sure that you are almost getting the same result. So you machined like 8 samples or 20 samples. You gave them to the machine shop and they machined them. Now, when you do the stress strain curve, you take the force over here and you divide it by the area over here. And that's how you calculate a stress. Is that right? Right. Now, what you want to secure is that, interestingly, we taught you that whenever you change the profile, you introduce stress concentration over here. So how comes that the sample doesn't fail over there? How? How? Well, one reason is because this is designed very nicely to minimize the concentration of the stress, and because this has a bigger dimension than this one, you still hope that the stress generated here is bigger than here, and for that reason it will fail over there. So failure will happen here. However, I don't want to make it a long story. What we usually observe, especially when we machine samples like these one, we are always careful with undercuts, just like the teeth. We go to the machine shop, so listen, I don't want an undercut. He will understand what you're talking about. Why? Because interestingly, if the machine shop didn't do a good job, you will take the sample, pull them, and all of a sudden, boom, you got failure over here. Another one, you get failure over here. Another one, you get failure over there. Another one, you may get one lucky failure in the middle, but the remaining keeps failing at the fillet. And do you know what is the story? It's very simple. The profile, the dream or the intended profile for the sample is supposed to go smooth like this. Now, there is a cutting tool, right? The cutting tool moves and it cut the sample profile with it. Now, in there is something with the machine. If you don't perfect it very well, if you don't control it right, you will end up, instead of having the profile like this, you may end up doing something like that. Now, that little tiny thing is invisible. You can't even see it. But if you look at it under the microscope, there is an undercut. Undercut means you cut it under the profile that was intended. And there you go, you get failures over there. So you take it to the machine shop, you throw it, and you tell them, come on, these are all garbage. And you did it, not me. This is an undercut. This is a problem in your machinist or in your machine, either way. So gears, teeth, undercut can be a problem. And we have a whole section about machining and so on, which is reading section 0.8. I think there is enough material there, but this is the concern behind the undercut. Now, what we want to do next is to move to parallel helical gears. Now, for parallel helical gears, what do we do? First of all, the helical gears are designed such that their operating shaft are parallel. So this is how they look like here, and they are parallel in here. Okay, that's one thing. The other thing is, what you need to understand is that the helical gears, as we saw in this example, are usually cut with an angle. We'll call it the helix angle later. And when you engage two teeth, two gears, you need to make sure that one of them is right-handed, the other one is the left-handed. That's why this gear is cut like this, and the other one is cut like that. Okay? That's number one. Number two, with the complexity of helical gear not being straight and it is inclined, and this one is right-handed and the other one is left-handed, you can still achieve an involute, which is called involute helicoid. Helicoid, okay? And I'm not going to talk about the details on how to construct the involute. You can read it by yourself and from the textbook. But what is important here is that this involute, which is achieved to maintain the same target, constant angular velocity ratio, and so on, is that when you look at a spur gear, ya shabab, the main difference is this. With a spur gear, we have a face for the teeth, or faces for the teeth, and when the other gear come in contact, is actually, it touches here, the whole line. So the other gear is like this. You understand? And what happens is, we look at this point of contact, but in reality, behind it, there is a whole line in contact. And this line goes up or down, depending whether the engagement now is to go down or up. That's another thing. Okay? Now, of course, ya shabab, this is probably makes sense now to you why with a spur gear, we said when we compare a spur gear with helical gear, there are differences in the smoothness, engagement, and so on. Because in reality, with a helical gear, the contact is one single point. It's not a line. The two gears, one of them is inclined this way, the other one is inclined the opposite way. And when they come, they touch at one point, and then they continue, and then they leave. And it just add up, right? When you have two surfaces touching, it's different than when you have 2 points touching. That's why the noise is less with the spur gear, okay? And it's just 1 point of contact. And of course, these lines of contact are parallel to the axis of the rotation, while with helical gear, this is not the case. So it says here, this gradual engagement of the teeth and the smooth transfer of the load from one tooth to another gives helical gears the ability to transmit heavy load at high speed with minimal noise compared to spur gear. So that's why, ya shabab, if you go to the industry around you, I can bet that you will see way more helical gears than spur gears, especially in the industry. Okay. Now we know that the helical gear produce thrust, and somebody might find this very annoying, and it is in the expense. Noise, I don't care about noise because I am not going to end up buying very expensive bearing and I deal with this thrust load and so on. No, you can also, although we taught you everything on how to deal with the thrust load in terms of bearing, you can actually deal with it within the gearbox itself, like this. This is now a double, helical gear arrangement. And what is it going to do? It will just eliminate the thrust which is produced in one direction is being opposed by another one, same in magnitude, opposite in direction, and that's what helps you cancel out the thrust. Okay, now what do we want to do? We want to set up a few terminologies and understanding this angulation of the teeth. will introduce spontaneously يا شباب new terms that we need to understand. So in here, what do we do? First of all, we have here two lines drawn at the center of two adjacent teeth, and by doing so, automatically, يا شباب, we can have this line, okay, which is parallel to the rotation line of the gear, will mark the angle psi, which is the helix angle of the gear. That's number one. Number two, we can see that the difference between the two adjacent teeth, the center line of the two adjacent teeth, okay, is what يا شباب؟ طبعا يا اخوان I don't know if you see this very well, but what do we have in here? We have it's like if you look on from the top of view on this gear, you will see this and this point as two lines, and then these point as two lines. So they may appear like too many lines close to each other. Okay, but now what are we doing? We are kind of plotting the line at the center of the each tooth. Okay, now this is going to be a repeated interval, and it is called the transverse pitch. Okay, so the distance AC, this is A and this is C, is the transverse circular pitch, which is PT, in the plane of the rotation. So it is measured in the plane of the rotation. You can think of it this way. This is PT. So from one distance to another between two adjacent teeth. The distance AE, ya akhwan, which is from here to there, is called and it is, marked over here. Yeah, the circle is coming over there. So there is a little delay, but I was talking about this point here over there. This is called the normal circular pitch, which is PN, and it is related through the angle, the helix angle, to the transverse pitch by this relation. PN equals to PT cosine psi. Okay. Now, the distance AD, okay, so from A to D over here, all right, is the axial pitch. I think, no, yes, it is. It is the axial pitch, and it is related to the transverse pitch and the psi angle tan psi, as you see in equation 13.7. And then if we have the nominal diametral pitch, which is, if you multiply it by the normal, what is it? The normal circular pitch over here, okay, you will get pi, and then that will help you construct a relation between the normal diametral pitch with the helix angle and the transverse pitch.
Doctor, what is the difference between the small PN and the big PN?
This one, this one, yeah, Shabab, this is the normal circular pitch, right? And the capital P, let me bring it over here. It is P is equal to the number of teeth divided by the diameter, which is the diametral pitch. But it is here, what did we call? It's called the normal diametral pitch, and we'll talk about it inshallah later in more details. What is important right here is that we will just want you to understand a little bit of these terms, and then we will see how are they going to impact the design, the selection and sometimes, of course, the force analysis for the gears. The force analysis for the gears is what we are going to do in the last 4 or 3 sections of this chapter, which of course very important. We still think of gears as one black box that has forces acting on it, and then it produces different forces, and these forces are going to be transmitted to the shaft as well as to the bearing. So we still have a long ride to go through. Okay, so I'm gonna stop here. This is where I stop with the other section, and I think it's time to take the attendance anyway. So let's see. Okay. يوسف اليوسف
موجود.
ماجد العباد
موجود.
حسن سنتين. عبد الرحمن يا محمد
Yes.
عبد العزيز
يس
دوسري أحمد
موجود دكتور.
عبد الإله
يس دكتور موجود.
خالد
Yes, Doctor, present.
دكتور
يس
do you hear me? حسن العياش موجود.
حسن يا
آه،
خالد
Yes, Doctor, present.
مصلح سعود
حاضر.
عبد الله
يس.
سلمان
موجود.
يا سلمان are you here?
Yes, can you hear me?
فارس يا فارس
موجود دكتور.
طارق
موجود.
عمر with the other section مصطفى
موجود يا دكتور.
علي
موجود.
حسام علي
Doctor.
are you here? يا علي are you here? العمر
Yes, Doctor, I said. Yes,
اوكي
yes.
هاشم
Here.
سلطان
يس دكتور
سلطان where are you?
يس دكتور
نايف
Yes, doctor.
محمد
Yes, Doctor.
عبد الله الزهراني
Yes.
مشعل
موجود.
عرفات
Yes, Doctor.
خالد
yes دكتور.
مؤيد
حاضر.
علي and حسن
Yes, here.
دكتور
okay yes
دكتور I'm from the section 6
who are you?
عبد العزيز
where are...
يس بلادي
دكتور